Okay, let's work a few examples of estimating population variances and standard deviations with confidence intervals. So the first example. Due to the rise in part-time workers, it is believed that the average work week in the US is down to 35 hours. However, it's believed that the number of hours worked in a week is highly variable. A random and representative sample of 24 workers was collected, and they provided the number of hours they worked in a particular week. You calculated a sample standard deviation of 4.3 hours. Now let's find a 98% confidence interval for the population variance of the number of hours worked per week for a worker. Okay, so we want a 98% confidence interval here. So we know that alpha is 0.02. Okay? And we know that the sample size was 24. We collected observations of work week hours from 24 individuals. And we found that the standard deviation of those 24 individuals and their work week hours was 4.3 hours. Okay? That is, from the work week hours recorded for these 24 individuals, the sample standard deviation was 4.3 hours. We know that since we have a sample size of 24, the degrees of freedom is n minus 1, or 24 minus 1, or 23 in this case. Okay? So now what we need to do is go and look up a value of chi-square, okay, on the chi-square distribution. Remember what most textbooks provide for the chi-square distribution. So here's the chi-square for particular degrees of freedom, and here's what that distribution looks like. Okay? This is not a symmetric distribution. We can't use the same kind of rules for a z or a t distribution for this distribution. Okay? We can't just take the value in the upper tail and subtract off or take the negative of that value to find the value in the lower tail, right? This is all above 0. Okay? None of these values on this chi-square axis are negative. So we have to be a little tricky about how we find these two values. Okay? So we want 0.01 in the upper tail, and we want 0.01 in the lower tail. And we need to find these two values on the axis. Okay? So typically how books are set up is the books provide the upper tail value. Okay? So here we have an upper tail value of 0.01. If we go look up this, this value of 0.01 in the table, okay, we go over to degrees of freedom 24 in the row. So go down to row 24 and over to column 0.01 in the upper tail, and we should get a value of 41.638. Okay? But now what we have to do to find this value down here, we still are given only upper tail values. So we have to find this value, this area in the tail associated with 0.01 in the lower tail. Okay? That is 1 minus alpha over 2, in this case, 0.99. Okay? So value of 0.99 in the upper tail is associated with 0.01 in the lower tail. Okay? So we go over to row 24. Pardon me, 23. This is degrees of freedom 23. Row 23, column 0.99 in the upper tail, and that value is 10.196. Okay? So this is how we find values on a chi-square distribution axis. Okay? Not as straightforward as a t or a z, but it's still not too bad. Again, we're just looking to isolate upper tail values associated with these things on the axis that we want. Okay? So now we want to implement the confidence interval for variance. Okay? That confidence interval is the variance is in between n minus 1 times s squared in the numerator on both sides. And in the denominator, we have the chi-square values. Okay? So the one associated with alpha over 2 in the upper tail is a larger value. Okay? The one associated with 0.99, 1 minus alpha over 2 in the upper tail, is a smaller value. So naturally, to get the larger upper bound, we need to divide by the smaller value. Okay? So this is chi-square of 1 minus alpha over 2 in the upper tail associated with a particular degrees of freedom. Okay? Likewise, to get a smaller number, the lower bound, we need to divide by the larger number to get a smaller overall number. Okay, so we need to divide by this number. This is chi square with alpha over 2 in the upper tail with a particular degrees of freedom. Okay, so let's implement this. We now have everything that we need to know to find this confidence interval. That would be n minus 1, 24 minus 1, times s squared, okay, 4.3 squared, divided by the chi-square in the upper tail. Pardon me, the chi-square in the lower tail, 10.196. Okay? And then this value right here, this is 24 minus 1 times s squared, 4.3 squared, divided by the value in the upper tail, 41.638. Okay? Whenever we do that, this is just arithmetic at this point, we get a value on the lower bound of 10.21 and on the upper bound 41.71. And that's in hours squared because we are bounding the variance. So what does that say? Based on our sample of 24 workers, the variance of hours worked in a work week is between 10.21 and 41.71 hours squared per week with 98% confidence. Okay? If we don't like dealing with hours squared, that doesn't make any sense to me. I don't know what hours squared even means. We can take the square root of both sides. So we could bound the standard deviation, the population standard deviation, to between the square root of 10.2, which is 3.2, and the square root of 41.71, which is 6.46 hours. So what that says is with 98% confidence, I believe the true population standard deviation of hours worked during a work week is between 3.2 and 6.46 hours.